Welcome to the Rutgers University Experimental Math Seminar. Today's speaker is Alejandro Morales and William C. William C. is probably your first talk, or you already gave seminars?
I went to, I presented at the Primes conference, but I think it's my first.
Oh, maybe not one of the first talk. And talk about something very interesting about the combinatorial aspects of the so-called Cry identity. Go ahead and share. Thank you.
Thank you very much, Doran, for the invitation, for inviting us, William and I, and letting us give the talk together. It is great to give a talk about this polytope to this audience. Doran has been very influential in this work, and we'll talk about that. So this is a joint work with William Shi, who is he's here and he's in Northview High School, so high school in Atlanta, and he's on his way to Harvard next year. And this is part of the Primes USA program of MIT, which is actually a research program that it's virtual because you match people from students from anywhere in the country with us. And then so I guess when the pandemic started, the organizers asked us if there was going to be some impact, and I said, well, we'll just continue meeting online. And I'll mention some connections of some joint work at the beginning with Carolina Benedetti, Chris Hanusa, Pamela Harris, and Anthony Simpson. And please stop me if there's any questions. So I guess I was trying to pick up an activity during the pandemic, and I thought juggling would be a good one. And there is this really nice book of Ron Graham and Percy Diaconis on which is green, so it doesn't work well with my green screen, on the magical mathematics. And there's a chapter about juggling and the mathematics of juggling. So a juggling sequence is a sequence of arcs specifying the amount of time a ball is thrown. So, for example, if you have three balls, maybe then a 3-ball cascade is you throw a ball to height 3, and you keep repeating this pattern, and so on. And then if you so this represents kind of time, and then if you like, if you can label this to be the hands, for example. Okay, so you would throw kind of so that you could throw a ball with a different height. So, is it clear what a juggling sequence is? We'll see them in a second. So let's start with one ball. I guess we should start with just one ball. So in how many ways can you juggle one ball with time n? So I'll start. Maybe I'll try to make this interactive. So if you have one ball here, time 1, you can only do this. So this is the only possibility, yeah? But how about with time 2? What are the possible options? So you could repeat what I just did, but what else could you do? So this is this, but what else could you do? You could throw a ball like higher to time 2. So you could do, instead of doing 1, 2, you could do 1, 2. Yeah, is that clear? So there's one configuration, here there's 2 configurations. And how about with time 3? So let me draw a little bit of these like the things we've seen already. So you could do 1, 1, 1, and you could throw a ball time height 2, and then height 1. And what else could you do? Maybe I could see the chat if you have.
So if you do it with n equals 20, you will probably get the password of the seminar.
Well, we'll see. We'll see what you get. Yeah. Well, I think the password will appear, but not quite yet. Yeah. So what other configurations could I do here? I could do kind of the reverse of this one, where you throw it height 1 and then height 2. Yeah. So I'm trying to do this at the camera with my ball if you want to see. Or you could throw something really high to time 3. So like 1, 2, 3. So there's 4. And then maybe if you enter this on the OIS, or you can see there's 2 to the n minus 1 ways, and you could try to find a bijection with sets or something that you like. Okay, so any questions with this problem? So you have 2 to the n minus 1. Okay, good. Let's try more balls. So in how many ways can you juggle t balls on time n? Okay, and these balls are, despite the picture, think of them as being the same, indistinguishable. Okay, so let's see with 2 balls and time 2. So you could do, and here in gray are all the possible throws. So you could do 2 balls at the same height, or you could do 2 balls that are thrown kind of high, or you could do a combination. You could do one that gets thrown low and one that gets thrown high. Yeah. And here, I guess you could think of left, right, but you could also think of just one hand. Maybe that's not so important. Okay. So do you agree that there's 3 of them? Yeah. So the balls are indistinguishable. Okay. So there's 3 here. We just saw them. With n equals 3 and t equals 2. I mean, what do you think? What is your guess, maybe based on what we've seen before? So maybe you could think, well, maybe it's 3 to the n, so that would mean there's 9, but there's one more actually, which is this one. You could have, so the balls are the same color, but just so that the balls you could have this kind of, they could have this kind of like crossing. Okay, so in total there's 10. Okay. Then surprisingly, there's no nice known formula in general. So let me tell you, then, when there's no nice formula, you can get some bounds. So let me tell you some bounds. So, well, that 3 to the n, you remember that the guess here was that it was 9. That 3 to the n is not so bad. It actually is a bound. So when t equals 1, we get 2 to the n minus 1, the answer from before. And the upper bound, and this is a good place to mention this, the best bound I know is this. So some product, and this comes from, this t plus 1 to the n comes from like tuples of sets. So before we had 2 to the n minus 1, 3 to the n minus 1 are like 2 sets, one containing the other, like chains of sets contained. So anyway, some tuple of sets. And this connection, it comes from a connection with alternating sign matrices that Doran very beautifully enumerated. But that it shouldn't be clear why that's true, but just to tell you how somehow it gets pretty sophisticated once you start adding balls. Okay, so having lots of balls is difficult. So a passage of that book is it says that to begin, it is necessary to have some reasonable objects to juggle. Some jugglers fill tennis balls with sand or some kind of grain. So and you see this beach here, probably in the sands of La Jolla in San Diego. So this maybe suggests maybe we could do a generalization. So instead of juggling more balls, we could juggle one ball made of sand. So like a real juggling, and that's really not real, but okay. So we're gonna juggle sand. Okay. So for example, you could have 1/3 of a ball here, 2/3 of a ball here. Okay, so the kind of and then here. Okay, so imagine you start with one ball of sand, and at the end the ball has to kind of build back again. Okay, so it's a weird generalization. But if you look at the set of these real juggling sequences, it's actually a convex object. It's a polytope. And in this particular case, for this configuration, you get a simplex. And then the vertices are the 4 configurations we saw before when we were doing 2 to the n minus 1, where you throw a ball like short times, short, high, high, short, and really high. Okay. And then this particular case here is somewhere in the middle. Okay. So any questions so far?
To the sequences, even for 2 balls, is a difficult sequence.
The sequence for 2 balls has an okay generating function. Yeah, but yeah, that's a good question. So this thing from before. So this satisfies a sequence, satisfies a recurrence with, maybe I should switch colors, with the number of turns is the partition of t. So as t grows, you get, this is the number of integer partitions. So maybe that gives you a hint of how. So it's a recurrence, but the number of terms is e to the square root of, it's like it grows super polynomially.
So for each t is a nice answer, but it's getting less and less nice.
Yes, exactly. Yes. Yes. Yeah. Good question. Yeah. Good point. Yeah. Thank you. Okay. So we get, so when we juggle sand, we get this nice convex object, which is a polytope. So let me just remind you what a polytope is to understand this better. So you can think of a polytope, and all our polytopes are going to have integral vertices. You can think of it as the convex hull of finitely many vertices in Zn, or the intersection of finitely many half spaces. And these are equivalent. So for example, in a cube, you could think of it as the convex hull of all binary sequences, or you could think of it as x1 up to xt, where every xi is between 0 and 1. And that would be the second description. Okay, just a little crash course to remind you of polytopes. So let's again think of our juggling. So I have one ball that's made of sand, okay? So why is it a polytope? Because, well, every possible throw, it's like this edge here in this network. So every possible throw should be non-negative, because you can put some non-negative, some amount of sand on each edge. And now you start with the one ball. So if you think of the first throws you do, this, you know, this better be this plus this better be equal to 1, because you start with one ball. And now in time, at time 1, or they say this is time 0, at time 1, well, you can throw x23 to height 1, x24 to height 2, but that better be equal to what you received from here. So this plus this better be equal to this. Yeah? So all the sand that gets in here gets preserved, okay? And same here. So what you throw here better be equal to what you receive from here. So x34 minus x13 minus x23 better be equal to 0. And then finally, the whole ball of sand has to reconstitute at the end. So this plus this plus this better be 1. Sorry. Okay, and this is, if you look, this is basically a bunch of inequalities describing your polytope. So it's the hyperplane description of your polytope. Okay, so you could think of now, if you look at this picture, you could think of, you have the complete graph drawn in this funny way, directed from left to right, and then you could think of the sand as flow, and so you have flow on your edges, which is the sand you're throwing, and then the first, you have 1 unit flow at the beginning, 0 at every internal vertex, and -1 at the end. Okay, but then you can the graph doesn't have to be the complete graph. You could like maybe forbid some edges. So maybe you don't allow to throw at height 3 or something like that. So you could have a graph instead of the complete graph. And your net flow, this vector, instead of being 1, 0, 0, -1, it could be something else. But we're going to focus mostly on 1, 0, 0, -1. So a flow polytope is you assign a non-negative number to each edge, and then the net flow condition at vertex I is that it should be AI. Okay, and that's a polytope. And most of the time we're going to focus on this case. Okay, and this was the case of one ball. Okay, of juggling sand. Okay, and we got the simplex from before. Any questions? Okay. So flow polytopes appear in lots of other fields. Maybe say in toric geometry, in algebra related to residues, in cluster algebras, in root systems of Lie types. They also recently have appeared in connections to diagonal harmonics, to other families of polytopes called generalized permutahedra, Schubert polynomials. So lots of really nice things. So hydra permutahedra. So here's a list of references. I'll send the link, the slides after if you're interested. So here's just a list of things, and there's relation to alternating sign matrices, juggling sequences. Well, I think that's pretty clear from what I'm talking about right now. So anyway, so lots of things. Okay, but let's tie the more balls with the real balls. So remember, JS and T is how many ways can you juggle T balls with time n? Okay, so when you have n equals 3, here is the network of throws, and if you have T balls, well, that's just saying, oh, I want instead of that's I want T. I have T balls at the beginning. In the middle, there's no balls, and here I have minus T at the end. And what you're counting is you're counting lattice, like you're counting integer flows. Okay, so because when you have, so if you look at the real juggling, if you want to get back to the original problem, you force things to be integer. You force to have whole balls. Okay, so basically these problems are connected. The number of juggling, the way of juggling T balls is the number of lattice points of the flow polytope. So basically the points that are. So there's two things here that I want to point out. You count lattice points, and T balls are encoded by just having in the net flow instead of being 1 0 0 minus 1 is T 0 0 0 minus T. But having T is just dilating. It's just dilating the original polytope. So even though it seemed like kind of far-fetched, when you're juggling one real ball, that if you dilate that, you control juggling more balls. Okay, does that make sense? So is that clear? So like if we saw a simplex, right, when we were juggling one ball, if you want to juggle two balls, you just dilate that simplex.
Yeah, Alejandro, I'm not quite confused. The x's are real numbers. So how do you get integers?
Yeah, so if I exactly, so yeah, right. Here in the original one, they were non-negative real numbers. But if I impose them to be integers, so if I just count the lattice points of that object, so if I count the lattice points, I recover this count.
Okay, thank you.
Thank you for the question. So for example, if you count the lattice points of this case with net flow 2 0 0 minus 2, it has 10 lattice points, which were those 10 configurations. Okay. So because we got to lattice points, let's review that a little bit. So here is the definition number of lattice points, and sometimes it's called discrete volume. So for example, for this simplex, which is there's 3 lattice points. And oh yes, sorry, I jumped. So when you start dilating your polytope by T, and you count the lattice points, the function that counts the number of lattice points is a function of T, the parameter that you're dilating. That's called an Erhard function. And if your polytope has integer vertices, it happens to be a polynomial. So this is called the Erhard polynomial. So it's a nice function. So for example, if you do it for the simplex, if you dilate the simplex here, the number of lattice points is given by a binomial coefficient. Because you're counting kind of like integer configurations that are less than or equal T. So it's like this kind of dots and bars problem. So it's given by a binomial coefficient. And that's not what I want you to emphasize, is that this is a polynomial in T. So it's a nice.
The fact is, polynomial is not an obvious fact, right? It's
not an obvious fact. Thank you. And this is a theorem. Yeah. So this is not an obvious fact. So thank you. And this is in part because you have integer vertices. Yes. Thank you, Doran. Yeah. So it's not clear, but in this particular example, you can see at least that you get a polynomial. Thank you. So for example, for the cube, if you dilate the cube by t, then the number of lattice points is t plus 1 to the d. So when t equals 1, you get 2 to the d. So it's another example of a polynomial there. And then just historically, the number of, so let's go back to flow polytopes. The number of integer flows of a flow polytope, it's called, it has this name KGA. And the reason for that is because it's a last name of someone, so it's a last name of Bertram Constant. So when you have the complete graph, this is called Constant's partition function. And let's see why it's, let's understand this term here. So here is the complete graph on 3 vertices. So let's count how many integer flows there are with net flow 1, 0, minus 1. And we've already done that. That's the juggling. So you can send one ball here, one ball here, or you can send one ball here. Okay, because I'm doing integers. I'm doing integer counting flows. So I can do one ball here, 0 balls here, or I can do one ball here, 0 here, 0 here. And so it's called a partition function because you can think of the vector 1, 0, minus 1, and you're breaking it into 1 times the vector 1, minus 1, 0, plus 1 times the vector 0, 1, minus 1. And how did I get these vectors in blue? Well, this edge goes from vertex 1 to vertex 2. So I have E1 minus E2. And this edge here goes from vertex 2 to vertex 3. So I have E2 minus E3. Okay, and here in this other configuration, I have 1, 0, minus 1. And I wrote it as 1 times 1, 0, minus 1, because I go from vertex 1 to vertex 3. And these vectors, EI minus EJ, are important in representation theory. So that's why it has that's why this connection comes from. And you're partitioning because you're partitioning the vector 1, 0, minus 1 into these vectors. You're seeing how many ways can you write it as a combination of these EI minus EJs. So that's where that comes from. Just some history, but so we said that lattice points of flow polytopes are difficult because they're counting these juggling that I told you was difficult, juggling t-balls. However, if you look at a generating function of these integer flows, when you sum over all possible net flows, you do get a product formula. And where does that come from? For every edge, you have this product. And it looks kind of scary when you first look at it. It's difficult to extract coefficients, but to understand the intuition for this is, well, if you're considering all possible net flows, then you're allowing all possible flows on an edge. So for each edge, you either have flow 0 or 1 or 2 or 3 and so on. And if you sum all the contributions, you get a geometric series. Okay, so the hard thing is extracting the coefficient, but it's all there. So you can use Maple to extract coefficients or Sage, and you in principle can compute these juggling or these lattice points. Okay, and then in representation theory, there are these formulas for important things like weight multiplicities or tensor product multiplicities in terms of this, but that's not so important. Just it's important in this field. Okay, and just recall the connection. So that counting how many ways can you juggle t-balls in time n is just counting the number of lattice points of the flow polytope. Dilated by t, and that's difficult. Okay. Okay, so counting lattice points is difficult. So let's look at the volume. And now from now on, it's kind of all about volume more or less. So when I talk about the normalized volume, I mean the Euclidean volume times the dimension factorial. So for example, for the simplex, the Euclidean volume here is 1. Here, the Euclidean volume is 1/2. And here is 1/6. If you remember, the tetrahedron has volume 1/6. But if you scale by the dimension factorial, you get 1, 1, 1. So the simplex is like is like the unit volume. unit normalized volume. And the reason we like this is because it becomes an integer, and we like integers. They count something, okay? So let's look at the real, like taking one ball, juggling one ball of sand, okay? This is a polytope, okay? Here we get a simplex. Let's calculate the volumes. So we get the sequence 1, 1, 2, 10, 140, 5,880. And maybe someone can tell me what's the handle in the OIS for this. But do you notice any patterns here? And I think this sequence was added by Neil Sloan, who's here in the audience. So do you notice any patterns? Unless you know, but if you know the answer, don't tell. Do you notice anything about this sequence? Anything? And I can check the chat. Or you please unmute yourselves if you notice some patterns. Or if you tell me the OAS.
The ratio.
Consecutive Catalans, right? One
Right,
times
so,
5.
right. There seems to be some divisibility. So,
Yeah.
so 2 divides 10, 10 divides 140. So what happens if we compute this ratio? We get 1, 2, 5, 14, 42, and these are more recognizable numbers. So indeed, this Vn is the product of consecutive Catalan numbers, and this was shown by Doran in 1999. And Cn is given by the Catalan numbers, so they have this nice formula. So the Catalan numbers count more than 200 objects, like dig paths, triangulations of n-gons, and there's this nice memoir by Richard Stanley about them. However, there is no combinatorial proof of this, like bijective proof, say, of this volume formula that Doran did. So, and the motivation, in some sense, is to find one. Okay, so we've gone a long way to get to these flow polytopes with juggling. So the lattice points are hard, but the volume is this beautiful thing. So let's talk about the proof. So remember that the number of lattice points of a flow polytope has this name, historical constant partition function. So there is this result that I like to call the fundamental theorem of volume of flow polytopes that says that the volume of the flow polytope at 1, 0, 0, minus 1 for any graph is the number of lattice points of the same graph, but slightly different net flow. And that net flow is the in degree minus 1. So this is a very surprising result because you're comparing Euclidean volume in some sense, or this is normalized, but with discrete. So you're like, it's telling you that apples equal oranges. So okay, so let's look at an example. So here's a graph, here's the flow polytope. And maybe, can you tell me what's the volume here? Can you tell what the volume is? Like, you should kind of divide by simplices and count simplices. So how many simplices do you see there? There's 2, right? So the volume is 2. So let's verify this. So it says that you should count integer flows on the same graph, but with in degrees minus 1. Okay, so let's calculate the in degree. This is in degree minus 1. So here we have 0, 0. That's the 0 here. What's the in degree here? Someone maybe unmute themselves. What's the in degree here? I have 1, 2. So this is 2 minus 1 is 1. Okay. The in degree here is 2. So 2 minus 1, 1. And then by conservation of flow, this should be minus 2. So to calculate my volume, I need to count integer flows with that configuration. Okay. Okay. So if this has net flow 0, all these should have 0 flow because nothing is coming out of there. And now there's a 1 here and nothing incoming. There's a 1 here and nothing incoming. So I can either put 1 here and nothing here, which forces this to be 2, so that 2 minus 1 is 1. Or I put the 1 here and nothing here and 1 here. Okay? So there's 2 configurations and the answer is 2 like it is. Okay? So this result reduces the volume calculation to a lattice point calculation. So for the complete graph, and this polytope I forgot to tell you, is called the Chan-Robbins-Yuen polytope. who conjectured the volume formula that Doran proved. So in that case, you should count the number of lattice points of the complete graph with net flow 0, 0, 1, 2, 3, blah, blah, which is what you get when you look at the in degree of a complete graph minus 1. Okay. And so then, okay, so then because you have in degree 1, 2, 3, sorry, and so on. Okay. And then Doran used this interpretation, and he said that this value is the value of this constant term identity called the Morris, his version of the Morris constant term identity. That if you calculate the constant term of this, that's equal to this product of gamma functions. And remember, the gamma function is like a generalization of the factorial. Okay. And when you plug in A and B and C equals 1, you get the product of Catalan numbers. Okay, so the proof is beautiful. It comes from this constant term, but that's why it's not so clear why the Catalan numbers are appearing, but it's there. Any questions? Okay. And I have some time, so here is Doran's entire paper. So it's really great. So, and here you see that the answer comes the Catalan numbers. Okay, and William's going to tell us like what's in here. Yeah, so I'll let now my co-author William to continue. So. Can you share your screen?
Yeah, can you see my screen now?
Yes, yes.
Okay, thank you. Professor Zeilberger proved that if we take the volume of this polytope, it's the sum of constant partition functions here, which is this product of consecutive Catalan numbers. So he also proved a refinement of this, which in this remark that said that if we force there to be K0 flows going to the sink, then we can actually refine this product by breaking up this largest Catalan number into a sum of Narayana numbers. And just to give a reminder, the Narayana numbers, they form this refinement of the Catalan numbers, where if we sum them, then that's going to give the Catalan numbers. So for example, if we interpret the Catalan numbers as counting the number of dict paths from 0, 0 to NN, then the Narayana numbers would count the number of dict paths with the specific number of peaks, like K. So for example, if N is 3, then we see that there's one path with 1 peak, 3 paths with 2 peaks, and 1 path with 3 peaks. So N3, 1 would be 1, N3, 2 would be 3, and N3, 3 would be 1. And Professor Mészáros also showed that if there's these collections of interior disjoint polytopes that make up the polytope, where if we take the total volume of each collection, that's also going to have this same volume formula. So we kind of have this lattice point interpretation in terms of these constant partition functions by forcing certain numbers of these edges to be 0. And we also have this interpretation by breaking up the polytope into smaller polytopes. And okay. I can't really write anything I said, but so basically we have this like volume for the polytope being a product of Catalan numbers, but there's actually a larger family of field polytopes also with volume given by the Morris identity. So the Morris identity is shown here again for reference, but we can actually construct a combinatorial object where that like uses all 3 of these parameters A, B, and C. So if we define if we define this graph K plus 2 ABC as the graph with vertices 0 to n plus 1, where 0 is the source and n plus 1 is the sink, and we say that there's A edges between the source and any internal vertex, B edges between any internal vertex and the sink, and C edges between any two internal vertices, then we Corteel-Kim-Mészáros showed that the volume of the flow polytope on this graph is equal to the Morris identity. So essentially, we can turn the complete graph into this multi-graph where the multiplicity is controlled by these three parameters, A, B, and C. And that's also going to factor into this more general volume formula. And as a corollary of the fundamental theorem for volumes of flow polytopes, that's also going to be equal to this constant partition function where the net flow at vertex I is in degree -1, and we can compute it to be this expression. So we kind of had this outline at this point where we had this volume formula for the Cry polytope being given by Mn111, which is this product of consecutive Catalan numbers. And we had this refinement proven by Professor Zeilberger that breaks that largest Catalan number into a sum of Narayana numbers. And we had lattice point and polytope interpretations for this refinement. And in addition, we just saw that there's also this larger family of flow polytopes that have their volume given by the Morris identity as well. So at this point in this table, there's kind of this large empty spot where this might lead us to ask, is there a similar refinement for this more general family of flow polytopes on the graphs Kn plus 2 ABC? And if there is there also combinatorial interpretations in terms of lattice points and polytopes? So to answer this question, we look at this refinement in the work of Baldoni-Vergne. And the motivation for this was in Professor Zeilberger's original paper, he used a different form of the Morris identity because in Morris's original paper, the exponents were all positive, and Professor Zeilberger said that if you use this shadowing technique, you can also get it to hold for negative exponents. And so Baldoni-Vergne defined this constant term phi and k ABC, and essentially this takes the Morris identity constant term and inserts this e sub k here, which is the kth elementary symmetric polynomial in n variables. So when k equals 0, this will reduce to the Morris identity. But they were able to compute an explicit product formula for this constant term that kind of refines, it gives a more specific version of the Morris identity. So we might be wondering, is this generalizing that refinement given by Professor Zeilberger for the Cry polytope? But if we plug in A equals B equals C equals 1, this is not equal to a single Narayana number times a product of Catalan numbers. And we said that refinement is not really a special case of this formula. And by the way, the proof for this identity, it used several recurrence relations. This was the most non-trivial one, but it was also raised as a question in the recent paper by Corteel with Mészáros and Kim, whether we can use that geometric interpretation of MNABC on that more general flow polytope, and whether we can combinatorialize these recurrence relations, because that would give a combinatorial proof for the volume of the Cry polytope through proving the Morris identity combinatorially. So if we go back to this outline, we still have this empty spot because we haven't really found a way to generalize this refinement. So to try again at generalizing that, we define this new constant term psi n k ABC, and essentially we take the Morris identity constant term again, and we add this term here, 1 plus t xi over 1 minus xi, and then we take the coefficient of t to the k. So we're essentially taking txi over 1 minus xi k times. and summing over all the possible ways of doing that. So the motivation for this term was, again, from Professor Zeilberger's paper. There was a remark that this term is related to Aomoto's extension of the Zeilberger integral. So yeah, that was the motivation. And we're able to compute an explicit product formula for this constant term. And this does have that Narayana number refinement as a special case if we plug in A equals B equals C equals 1. And our proof also used several recurrence relations, and this was the most non-trivial one. We tried to take a combinatorial approach to the proofs, but this identity was proven using some symmetric sums, and the fact that if we take the residue of the partial derivative of an analytic function, that's going to be equal to 0. And there's interesting symmetry here with the k's and the n minus k plus 1 and the b and the a minus 1, but it's not really clear how to prove this combinatorially. And if you also recall, we were motivated to kind of give this a geometric interpretation. So to do that, we need to generalize this graph even further by adding a parameter s, a subset of the set from 1 to n. So we take the graph CAM plus 2abc, and we add n edges between the source and the sink. And for each vertex I in our set, we're going to delete an incoming edge from the source and an outgoing edge, add an outgoing edge to the sink. So for example, if our set here is 1, we go to vertex 1, because remember the source is 0. And then we're going to delete an incoming edge and add an outgoing edge. And for any vertex not in our set, we're just going to leave it as it is. So are there any questions at this point?
So do you have a combinatorial proof of the previous slide? Or is it
Sorry?
Do you have a combinatorial proof in the previous slide?
Oh, no, this relation we were not able to prove fully combinatorially.
So it's still an interesting open problem to get.
Yeah, it's still an open problem to prove this with converts. Our proof used some analytic aspects.
Thank you.
Yeah. But okay, so we're able to show that if we take the flow polytopes on these graphs and we take the volume of those flow polytopes over all k element subsets of the set from 1 to n, adding those volumes is actually equal to this constant term psi n k abc. And we see that when a equals b equals c equals 1, this simplifies to Mészáros' polytope interpretation for the refinement for the Clyde polytope. So if we do an example, so this identity is here again for reference. If we look at when, say, n equals 2, there's going to be 4 possible sets. So this was the one we just saw where the set is 1. We could also do it where the set is 2. And instead we go to the second vertex, delete an incoming edge, an outgoing edge. And we can group these 4 different flow polytopes into collections based on the size of that set. So for example, it could be the empty set, or there's 2 sets with cardinality 1, and there's 1 set with cardinality 2, which has both vertices. And the volume of each of these is given by this constant term psi. So it's not necessarily that the volume of each individual polytope is nice, but we can group them into these well-described collections, and they together have a nice volume. Okay, so in the to kind of give some intuition for the proof of this, and also you might be wondering, why do we add n edges between the source and the sink? So to kind of give some intuition for that, there's this subdivision lemma in the work of Posnickov and Stanley, and this allows us to reduce a flow polytope to 2 interior disjoint polytopes. So if we have edges x and y, we can split this into 2 disjoint cases. X is greater than or equal to y, or x is less than y. And we can create this map so that the net flow is preserved locally at each of these three vertices. So for example, the net flow here is x at vertex A, it's y minus x at vertex I, and then it's negative y at vertex B. And then we can check here that this is actually preserved. So here it's still y. It's y minus x at vertex I, and then it's negative y at B. So this kind of subdivides it into two disjoint cases. And if we apply this lemma on this flow polytope on K plus 2 A, B plus 1 C at each internal vertex with an edge from the source and an edge to the sink, then for each of these two possibilities, we see that either we delete one of these edges, and then we add an edge from the source to the sink. So if we're doing that n times, we're going to end up with n edges between the source and the sink. And additionally, since there's two options at each vertex, we're going to get 2 to the n children graphs. So that's going to correspond with the 2 to the n subsets of the set from 1 to n. And as we just saw on the previous slide, we can group them into collections. And as you can see here, like an easy way to think about the collections is in terms of Pascal's triangle. So for this row of Pascal's triangle, it would be like 1, 2, and 1. So that's one way to think of the number of graphs in each collection. So yeah, this is how we get this notion of equivalence, because when we subdivide this polytope, we get this. And as a corollary, if we like take the volume of both of these, we can get this expression here, because the volume of the parent graph is equal to this Morris identity by the work of Corteel-Kim-Mészáros. And if we take the volume of all of those 2 to the n children graphs, that's the same thing as summing over these collections by grouping them into n plus 1 collections. So we get that the Morris identity is equal to the sum of psi from k equals 0 to n. So kind of to summarize, we were able to fill out this table a little bit more. We have this new refinement of the Morris identity. We compute an explicit product formula and give it interpretations in terms of lattice points and polytopes. And we leave as an open problem to find a combinatorial proof for this last recurrence relation. So yeah, I think that is all.
Thank you very much.
Thank you very much. We have 2 minutes for questions.
Oh.
So I have a general question. There's something called the QMorris identity, the so-called Q analog. Is there any way to relate this beautiful theory and stick a Q into it?
Yeah, so that's a very good question, Doran. So, which actually I was going to ask you. So, you have this email where you outline the proof of your Morris identity using QMorris. So with a graduate student at UMass, William Dugan, we're trying to get a shadow version of QMorris, but it's work in progress, and maybe we need to ask you some questions. So, but it seems natural to find a Q analog. I mean, there is a Q analog of the constant partition function by Lustig, where you keep track of how many edges you use, but that doesn't seem to have a product formula, if at least for that Q analog. But yeah, but I might send you an email to ask you a question about that. Thank you.
Anyway, it's really beautiful, beautiful work. Any other questions? Let me make a comment. It's really beautiful, beautiful work. And congratulations, William, for speaking in a seminar for which at least 2 Nobel Prize winners and at least 1 Nobel Prize winner and somebody who should have gotten Nobel Prize, Freeman Dyson, spoke in the same seminar. If you look at the archive. So one day, maybe in 20 or 30 years, I will brag that William C. spoke in my seminar. Thank you very much. And also Alejandro.
Thank you, Doran. That's very good.
Okay, thank you. Thank you so much.
Thank you, William. Sorry for drawing. I was trying to draw on your, but sorry.
Oh, yeah, it's
managed well. Sorry about that.
Yeah, no problem.
Sorry. Thank you for organizing and for hosting. Thank you,
Thank you.
everyone.